Hello guys, my name is Bob. Welcome to the Excel Math channel, and today we are going to talk about the chi-square goodness or fit test. We use this chi-square goodness or fit test to determine if our hypothesis that we kind of hypothesize is correct or not. All right, so let me give you an example on the chi-square goodness of fit and how do we apply this test. So let's say, for example, I have this whole thing, all right? This whole country A, which is square shape. And for country A itself, there are papaya trees that are distributed into different regions, all right? Let's say I divide this country into 4 different regions, and I think that, the number of papaya tree is the same in each region. All right, so I want to test to see whether my guess of, whether the number of papaya trees is the same in each region. So if I guess that the number of papaya trees is the same in each region, so which means that each regions will have 20 divided by 4, because total number of papaya tree is 20 and we have 4 regions, and I'm actually guessing whether or not we have 5 papaya trees per region, right? Versus our alternative hypothesis that number of papaya trees is not the same. All right, so in this case we are doing a two-tailed test here, okay? Because my alternative hypothesis is the number of papaya trees being not the same, and suppose that I set an alpha to be 0.10. You can set alpha as 0.05 and so on and so forth. It all depends on how, what do you want your significant level to be. All right, so in this chi-square goodness of fit test, all right, there's this formula that you can use, which is the sum, okay, of the observed, okay, number of papaya trees minus the expected number of papaya trees in each region divided by the observed number of papaya trees, all right, square, and each region. And this is the sum of the regions. All right, so because we have 4 regions, all right, we have 4 regions, okay, this whole thing itself, okay, we have 4 regions, all right? This whole summation of the squares of the observed minus expected over the observed follows a chi-square distribution. And because we have 4 regions that we are looking at, my degree of freedom is actually 4 for the number of regions minus 1. Okay, so the question a lot of people ask is, why is minus 1? Because the thing is that you are estimating, all right, this this parameter, which is the expected number of papaya trees in each region, all right, because you are guessing, all right. So the thing about degree of freedom is that if you are estimating, okay, a parameter itself, you have to subtract by the number of parameters that you're estimating, which is in this case you're estimating that the number of papaya trees in each region is actually 5, all right. So in this case, we have a chi-square statistics with a degree of freedom of 3. So next thing, let's just calculate this value itself, the sum. So the first region, we have 5 observed papaya trees, and then we subtract away 5 expected in each region divided by 5. So the second region, we have 7 papaya trees, and then we subtract away 5 expected papaya trees divided by 5. And the third region would be, we have 3 observed papaya trees minus 5 divided by 5 square. And the fourth region is 5 minus 5 divided by 5 square. Okay, so if you're to realize, okay, each of these actually is a chi-square distribution, all right? Each of these region follows a chi-square distribution with 1 degree of freedom, but then the thing is that because we are estimating one of the parameters, we have to subtract 1 away. So To calculate it, this is actually 0, this is 0. Well, 7 minus 5 over 5, that is 2/5. 2/5 squared is 4 over 25, plus 3 minus 5 over 5, so that is negative 2 over 5. You square it becomes a positive, so that is 4 over 25. And this gives you 8 over 25. So my chi-square statistics, okay, is 8 over 25. All right, so we are going to look at the 3 degrees of freedom to see whether this chi-square statistics falls outside the range itself, within the range itself. All right, okay, so we put as alpha is equals to 0.10, but the thing is that because it's a two-tail test, if we were to look at the distribution itself, it's actually something like this. All right, so here would be 0.05, here would probably be just 0.05. All right, so we are only looking at the alpha is equals to 0.05. So in this case, we have a table. Oops, we have a table down here. Let me just shift it down here. Okay, so we have 3 degrees of freedom. If we were to look at 3 degrees of the freedom at just looking at this table, it says that the probability of a larger value of x squared, all right? So it just means that it's probability that your this chi-square statistics is greater than x squared. All right, so we have to look at here. All right, because we set as 0.05 at degree of freedoms of 3, the probability that the chi-square distribution is greater than x squared is if we were to calculate here itself, okay, what is this value? This value is actually 0.35. okay, oops, okay, we calculate this value at 0.35, so which means that for this value itself is actually what, 0.35. all right, and this value itself probably is, if you were to look at 0.05, because we are doing two sides, and it's 7.81. So here is actually 7.81. okay, so this value itself is actually 0.32. all right, so it actually falls within the rejection region. all right, so because my rejection region is actually here and here. all right, so what I do is, because my 0.32 is actually lesser than 0.35, hence, okay, we reject, okay, the null hypothesis. That means it rejects my belief that the number of papaya trees is the same in each region, but instead, based on the chi-square goodness of fit test, okay, it concludes that, okay, the alternative hypothesis should be correct. all right, based on a significant level of 0.10. all right, okay, so that's about it for the chi-square goodness of fit test. Hope everything is clear from explaining, especially about why the degree of freedom is actually -1. And yeah, and that's it from me. Thank you guys for watching, and I'll see you in the next video. Goodbye, guys.